Let's look at some examples of transformations with different parent functions. What we're going to do is we're going to apply transformations to a parent function in writing the equation as well as graphing. So we've got an absolute value function, so the parent is y equals absolute value of x. And I'm going to be shifting 4 units down and 5 units left, and then a vertical compression of 1/2. So in my absolute value function, I know my shifts left and right have to go inside with the absolute value of x. So I'm going to start with y equals my absolute value of x shifting 5 left. That means I have to add 5 inside the absolute value. Then if I want to shift down, that means I'm going to be subtracting a number at the end. And that vertical compression is the number multiplied out in front. So it'll be 1/2 out in front. So my equation is going to be y equals 1/2 times the absolute value of x plus 5 minus 4. And then the transformations I see, this is left 5, this is down 4, and this is a compression of 1/2. So moving left 5 and down 4 puts my vertex at a different spot. Normally it would be at 0, 0 for my absolute value function. But it's not at 0, 0 anymore. It's now going to be left 5 and down 4, so -5, -4. So -5, -4. Now normally with my absolute value function, the pattern is to go over 1, up 1, over 2, up 2, over 3, up 3, and then I've got to create that V by going left 1, up 1, left 2, up 2, left 3, up 3. But I've got to use my vertical compression to change my ups. So I'm going to multiply each of my ups by that 1/2. So when I go to my vertex, I'm going to move over 1 and up 1 times 1/2, which is just 1/2. Then I'm going to move over 2 and up 2 times 1/2. 2 times 1/2 is 1. And then over 3, up 3 times 1/2. 3 times 1/2 is 1 and 1/2. So we get those points. Then I'm going to do the same thing going in the left direction. Over 1, up 1/2. Over 2, up 1. Over 3, up 1.5. Now remember that this gives me the nice V shape, so I'm going to connect those dots in a nice straight line that goes all the way to the edges of my graph paper and put arrows on them. How about a square root function? Square root is y equals square root of x. Now I always want to think about how those parent functions look before I start dealing with the different transformations I have. Well, I know on a parent function of square root of x, I start at 0, 0. This is the one that's the eyebrow. And I move over 1, up 1, over 4, up 2, over 9, up 3. Until you get used to what these parent functions look like, I suggest keeping your parent function packet that has all those parent function notes handy so that you can use your keys to graphing as you start each of these. Now let's look at our transformations. I'm going to be shifting 8 units left, 2 units down, vertical stretch of 2. My left goes inside with my x, down goes outside at the end, vertical stretch of 2 goes out in front multiplied. So when I rewrite my equation with transformations, I will have y equals 2 times for my vertical stretch, the square root of, shifting 8 left is x plus 8 inside, and then 2 down is subtract 2 at the end. So let's see how that affects when I graph. I'm no longer starting at 0, 0, because I have to shift 8 left, which would be -8, and 2 down, so -2. So I'll start from -8, -2. And instead of going over 1 up 1, over 4 up 2, over 9 up 3, I have to multiply each of those by my stretch of 2. So I'm going to be moving over 1 up 2, over 4 up 1, 2, 3, 4, over 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, up 6, 1, 2, 3, 4, 5, 6. And then I'm going to draw that eyebrow shape. Notice that it does look stretchier. It kind of looks like a surprised eyebrow now. Okay, let's go to the reciprocal function. This is probably the most challenging one to draw with transformations. Reciprocal function is y equals 1 over x. Now to shift left, that's going to go inside. To shift down, that goes added or subtracted after the function. And a stretch of 3 is multiplied out in front. So when I take those into consideration, I will be working with y equals a 3 out in front of my 1 over x. Shifting left 4 will be plus 4 in with the x, and shifting down 5 will be minus 5 afterwards. So you can write it like that, or you can multiply your 3 over 1 times that function. So you could also write it y equals 3 over x plus 4 and then minus 5. Now let's think about what that reciprocal function looks like. The reciprocal function starts with a black hole at 0, 0, and then it's got those force field lines going out of it. But this time my black hole's not at 0, 0. It's shifting 4 units left, so negative 4, and 5 units down, so negative 5. So that black hole is at negative 4, negative 5. And then I've got those force field lines coming out from the 4 directions around it. And then from there, from that black hole, I would move over 1 and up 1, over 2 and up a half, over a half and up 2. And then I would go the same direction, same numbers, left 1 and down 1, and then left 2 and down a half, and then left a half and down 2. But with my stretch of 3, I know I need to multiply all of my ups times 3. And all of my downs times 3. So from my black hole, I will be moving over 1, up 1, 2, 3. And then I'll go over 2 and up a half times 3, which is 1, 2, 3 halves. And then over a half and up 6. 1, 2, 3, 4, 5, 6. Now my graph still has the same general shape, so I've got to run along this asymptote through those 3 points and then turn and run along that asymptote. So that's one branch of my graph. Then I'm going to do the same thing on the other side of my black hole. So I will move left 1 and down 3, left 2 and down 1 and 1/2, and left 1/2 and down 6. And then draw the same picture. So I've got to run along this asymptote through my 3 points and along that asymptote. Let's extend that down there. Last problem on here, we are going to do this for the following f of x. Now remember what I said, f of x represents any parent. So in this case, my parent is x cubed. So what this equation is telling me is to do y equals 2 times the parent with subtracting 3 inside of it and a subtracting 5 outside of it. So all I'm really doing is taking this f of the x minus 3 and replacing it with the parent operation. The parent operation is cubing. So it'll be y equals 2 and then x minus 3 inside the function, cubing, and then minus 5. So what are those transformations? The minus 3 inside the function is going to shift the function right 3. The subtract 5 outside the function is going to shift the function down 5. And the 2 out in front is going to be a stretch of 2. So in my normal parent function, y equals x cubed, that's the squiggle graph. And it starts usually at 0, 0. But this one's not starting at 0, 0. It's going to start right 3, so 3, and down 5, so 3, negative 5. Then normally the squiggle goes over 1, up 1, over 2, up 8, over 3, up 27. And then it also goes left 1, down 1, left 2, down 8, and left 3, down 27. So I will start from 3, negative 5, and move over 1, up 1. Oops, I forgot to stretch. We have to stretch times 2. So times 2, times 2, times 2. And stretch your downs. Times 2, times 2, times 2. So I'm not going over 1, up 1. I'm going over 1, up 2. And then over 2, up 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then left 1, down 2. And left 2, oh gosh, down 16 would be way, way down there. And then when I connect these, remember it makes like a sideways, a parabola that's been twisted in the middle. So parabola to there and then twist around and make that parabola.